All right, well, welcome to class. Uh, this is fun to have a first snow day, I guess. I'm happy to see some snow for the winter. But it did complicate things for us, obviously, in this class. Since we only meet once a week, it really is important that we cover material this week. Otherwise, we just will not get to cover everything throughout the semester. And this first week is some contextual information, some review, and some kind of groundwork for the stuff that's coming later in the semester. It really is important. And so here's what we're going to do. I am going to cover this note set with you. This is chapter 1. I believe that this material is the most difficult and most conceptually important material of the 3 chapters that we'll cover this week, which is chapters 1 through 3 of our textbook. Oh, I should have brought my textbook in here. I didn't. Chapters 1 through 3 of the textbook. You are going to need a textbook, or you're going to need to share one with maybe a classmate. This is an advanced strength conditioning class. It is going to be a lot less intuitive than the 260 class. So, essentially in 260, we kind of learned the basics, and we are going to go much, much deeper now. You will see, even in just today's lecture, that, we'll go from like a kindergarten understanding of strength conditioning to, like grown-up understanding of strength conditioning, and what it really is to think scientifically about how we're going to train our athletes. So the material's not as easy as 260. There is some overlap for sure, but it definitely goes deeper. And so having a textbook or access to the textbook is going to be important as you go through the assignments. The assignments for this week are as follows. Number 1, you have one quiz per chapter that's covered in the textbook. These are the textbook quizzes, and they're pretty straightforward. So chapters 1, 2, and 3, that's 3 quizzes that I have made due on Sunday. They are not super long, and so they shouldn't, if you have the book and you've read the material and you're kind of familiar with it, it won't take you that long. The second set of assignments you're going to have this week are your note sets or your worksheets for chapters 1, 2, and 3. And what I'm walking through with you in this particular video is chapter 1's note sets. What do I expect in these note sets? I expect that you take notes, that you put your own ideas down next to the graphs, the words, the tables that I've put in here. Essentially, everything in here is a concept that we need to remember and take with us. And so if there's a graph, then I should see your notes next to it. If there is, a word to define, I should see your definition next to it. Of course, using the proper definition from the textbook. If there's some questions at the end, I can just scroll through here. Towards the end, I have added a few questions in this particular note set. So sometimes there's very clear questions, but even in these pages where there are no clear questions, I have left space for you to add your notes. Like, what is it that this graph is representing? And what is it I'm supposed to remember about this? Or how is it I apply this? So we'll go through this one together, get you guys started. Plus, I said, remember, it's pretty important background information, and there's a concept in here. It's pretty technical, and I want to make sure and cover that with you. Let's get started. So the very first thing we want to think about is the idea. Let me zoom out just one. The idea that the loads that we're giving athletes, we have to really think about them. What is the right load? Too much and too little are both not going to achieve the maximal amount of performance improvement that we're looking for. Now, this graph is conceptually showing us the difference between a trained athlete and a beginner, or a trained athlete and someone who's exercising for non-athletic purposes, maybe. And we're going to compare the 3 types of load categories that you could have. You could have The first one is a detraining load. And you can see a detraining load is the smallest on the x-axis, the smallest quantity of loading of the three. And this is a load that is inadequate to maintain your current adaptations. So even if you're training, you're losing fitness, you're losing ability over time, maybe slowly, but you're still losing. And the less and less load we have, the more and more the physical fitness is declining. So no training produces the fastest rate of physical decline, whereas, maybe this load is still declining, but declining slowly. We also notice here now the difference between the athletes and the non-athletes. Because an athlete, having trained, starts out at a higher fitness level, the amount of load for them that is detraining is higher. So an athlete could be detraining at this load here on this part of the graph, whereas a non-athlete might find that that is actually a training load. And you guys know this intuitively, athletes are going to train harder than someone who's non-athlete, or an experienced athlete will be able to train harder, will train harder than a non-experienced athlete. So that's detraining. The next one is retaining load. Retaining load is a load that is adequate to maintain but not improve. Retaining load is inadequate to maintain, hence the fitness level stays level. Fitness level stays level, but they can't at these loads get any better. Retaining loads might be really important and something we intentionally do. For example, during a season, we want to try to maintain the fitness level from the preseason training, but we definitely don't want to be trying to get more fit, because we might be focusing on our sports performance, our skills in the sports more during the season, which would be typical. And so a retaining load is the amount of load necessary to just keep what we have so we can play our sport. And of course, that's going to be a higher load. So you can see if I just draw a line down for an athlete, retaining load is where we might see a stimulating load for a non-athlete or a beginner. All right, so lastly is the stimulating load. And so these are the loads that will produce increases in physical fitness. These are the highest loads that we would put on athletes. And again, you see the pattern that athletes are going to have a higher stimulating load as compared to a beginner. Athletes need to be here, but to stimulate a beginner, it only needs to be here, and it only should be here. All right, so that is the first concept, is the three categories of training loads: detraining, retaining, and stimulating loads. All right, the next concepts over here are a bunch of terms. Now, these are directly from the book, or most of them are. I'm going to hit on just a few that I've added because they match up more with the NSCA textbook, so they kind of pull in ideas that you already know. But we're going to see here, a lot of these are really common. One of the things that I want to point out here is that this textbook is using some biological terms. So essentially, instead of talking about it in terms of the Hans Selye general adaptation theory, they're using some just typical biology words. And so accommodation and transformation are kind of new words for old concepts that you already know in terms of adaptation and the process of adapting. So take a look at those. Now, I wanted to also talk about the principle of diminishing returns. The book does kind of talk around it for a little bit, but it doesn't talk about it in too much detail. And this is a very important point for us as we move forward in the next chapters and next week. So the idea here is that the performance gains that you're going to get from something are highest when that thing is new to you. Now, this is the case when you go from a beginner to a training athlete. You will see dramatic increases really quickly. And you guys might have experienced that you can have a true beginner maybe double their squat or double their bench press in, a matter of a couple of months. But we would never expect somebody who's been training for 2 years to have the same experience that they would be able to double their squat in 2 months. That would never, ever happen. So the longer you train, or the longer you stay at the same training load, or the longer you stay with the same training methods, the less and less benefits you get over time. Okay, because once you're adapted, you're adapted. And so you need a new stimulus or a higher stimulus in order to get more adaptation. So this graph is a graph of the principle of diminishing returns. Make sure you understand that concept. All right, the next one I want to point out and pull out is the concept of genetic ceiling, because the concept of genetic ceiling, I have to get my markers here, hold on. The concept of genetic ceiling is not in the book, but I think it really fits well in this chapter, so I just wanted to bring it up. It is in a later chapter. And so basically, the concept of a genetic ceiling, I'm freehand drawing with my computer here, sorry. So if I create a graph here, and on this axis, I have, basically like fitness or ability. And so I'll just put fit. Barely legible. And over here, what I'm going to have is basically your training time. It's not just time because it's time plus training. So it's TR plus T. Is cursive better? Cursive is better. Time. Okay, so training time, how long you've been training, how hard you've been training over that time, consistent efforts over long periods of time. So let's say that this is like 2 years out here. And of course, we'll start with day 1 on over at the axis. 2 years. Cursive. It doesn't look like years. That says 2 years. Now, when you start out, your fitness, of course, is very low. Your ability is very low. And the idea of a genetic ceiling is a theoretical concept. We don't know where this is for any person. But in theory, a person has, like a genetic limitation. Humans can run really fast. We start out learning slow. We can train. We can get faster and faster and faster. But will we ever run 70 miles an hour? No, we don't think that's possible for any human. Now, each individual will have this theoretical limit for any particular measurement we come up with. And it might be affected by things like how long are your limbs? How tall are you? But then it can be affected by things that those you don't have control over. There are things that you do have control over, like muscle mass. Well, we could increase your muscle mass. So even though you're short, so your max speed might not be as high as we'd like, we could increase your muscle mass and increase your max speed. So in any case, this is our genetic ceiling. I'm just going to put GC here because I can't write very easily. So GC, genetic ceiling, the theoretical top of your performance, if you did everything right for a long period of time, what is the highest performance measure we could ever get from you? And then, so we start out really low, and quickly you come up. And so this is our law of diminishing returns. At first, gains come very quickly, and then they start to level out, and then they start to go to almost nothing. And it probably would take more than 2 years, but eventually you might be able to reach your genetic ceiling. You might be able to get to the place where we say, you've done everything right for as long as we can remember. As more theoretical than actual. But the idea of diminishing returns is that, within this one point of time, from this line to this line, we saw an increase of fitness, from here to here. But later on, when you are training out here and you have adapted a lot already, and I take this measurement of time from here to here, and I see that your fitness increases during that time are only from here to here. And you see that this line is just much shorter than that line. So diminishing returns. The closer you get to your genetic ceiling, the less and less and less your returns will be. The closer you are to your genetic ceiling, the lower your returns will be from any particular type of training. This is important because one of the things we're going to look at all semester long is what is the best way to train someone. And if I'm doing research on beginners and I give them this method of training and I see, oh my goodness, look, in just a few weeks, they had this much improvement in fitness. This is an amazing method of training. Well, yeah, that's true, I guess. It could be true. But if I apply that same fitness method of training up here, I might only get this much improvement. That doesn't mean it wasn't effective. It was just effective relative to where those athletes are in their, diminishing returns graph. All right. So we always want to pay attention to who was being tested. And then what is this really going to be this amazing if we use this in athletes who are already athletes? Most of the research out there is done on very low level athletes, which is why we know a heck of a lot less about the best ways to train high level athletes than we do about low level athletes. All right, so that's this piece here. You need to draw this graph and provide in the space a description of what's happening in there. Oh, interesting. How do I get rid of this? I didn't realize it would do that. Let's keep moving. I erased my screen. All right, let's move on. Next concept in here is the concept, and this is coming out of the textbook. There's a little breakout box that talks about how do we train an athlete knowing that we have diminished returns. If we have an athlete who's an Olympic, who's training on an Olympiad, in 4 years, there is their next really important competition, 4 years away. If I start now with this one training method and stick with that training method, even if it is a very, very good training method, if I try to stick with that one training method for 4 years, my athlete is going to get benefits initially and then plateau, at best plateau. And that's not ideal, because what I'd really like is for my athlete to continue to continuously improve, even by small amounts, for 4 years. And so one of the things we have to do is either not use the most effective training method in the beginning, or rotate a series of effective training methods over the 4 years. And also we'll of course add in things like recovery periods and things so the body can recover and we don't have buildup of injuries that are problematic. Read that little box on training for Olympiads and how we have to knowingly choose less effective training methods for part of those 4 years, or there's no way we're going to get the overall best results. If we go for just the highest best training method for 4 years straight, we will get an inferior athlete than by cycling through highly effective and less effective training methods throughout the 4 years. That's the facts. Okay, next one is where we get to the hardest concept of this chapter. I'm going to go slow, walk you through it, and hopefully you get it. Remember, you can rewind me and play me back, okay? Or reach out if you have questions after this. So the next concept is a very mathematical concept. As beginning strength conditioning coaches, as athletes yourselves, you do not have a full appreciation for how much data analysis should be going into every training decision that is made by your coaches. Should be. Not all coaches are even knowledgeable about this, but I want you to be the kind of coach who is. So the next concept we're going to talk about is the idea of measuring effectiveness in a very scientific way of any particular training method, and the concept of transferability. Now, the first thing to think about in transferability is the idea that we have two things that we're looking at. There's two things we're going to look at. We're going to look at the sports performance. Now, a lot of sports, especially team sports, you don't have one measure of, I can't, so hard. Sports performance, P. Um, in some sports, you have a single measure that's just the obvious answer. If I'm a shot putter and I want to know, have I increased, have I improved? All I have to look at is like, what is my, new PR in shot put? If it went up, I'm improving. If it's been weeks and months since I've had a PR, I'm detraining. I'm getting worse. In some sports, so track and field's a great example, very obvious. It's your height, distance, or time in your event. That's a clear measure of your sports performance. When it comes to team sports, because they're just more freaking complex, especially when you have defense and offense and all, like so many little aspects, you might have to pick out several different measures of what appropriate performance would be. And so, for example, on let's say basketball or soccer, we'll do soccer. If we do soccer, the number of goals per game is not a good measure because some games you'll have one or two, and some games you'll have zero as an individual player. So that's not going to be a good way to measure it because you could have been, playing amazingly today, but you just, we didn't run the plays where you get to shoot the ball. Um, so that can't be the measurement, but we could do things like sprint speed. Maybe because of the position you play, I really need you to get to the ball quickly and like out sprint the other player on the field to get to the ball. So a short distance sprint speed could be a sports performance measure that I would really be interested in for soccer. Or it could be, anything. You guys know your sports, the kinds of testing that might be appropriate for the different sports. But whatever it is, it's got to be sport like focused. Like this, having this physical ability will improve performance overall over time. The second characteristic we're worried about is the training activity. Let me try. There you go. Training activity. And so the training activity is the thing we do in practice or the thing we do in the weight room that we typically don't measure so much that is going to make you better at this thing. So this is the training thing we do in order to get better at this sport thing we do. Now, the training thing we do might be like plyometric training, or it might be a specific type of agility training, or it might be a specific type of sprint speed training, or it might be a specific type of weight room activity, any of it. So whatever it is that I'm going to do in training to try to increase the sports performance variables. All right, so those are the two things we have in common, two things that we're going to have to talk about here. And transfer is basically a measurement of how much this thing improves this thing. For example, I could take my soccer players and I could send them to yoga class for, 2 hours a week. And I could be like, our training is yoga, but how much does that make my athletes bigger, faster, and stronger and more dominant on the field? Yeah, questionable. Like it maybe at first, maybe a little. Or I could send my athletes to the weight room with a really great resistance training program. How much will that make my athletes bigger, faster, and stronger on the field? Maybe quite a bit more. So the transfer of the weight training would theoretically be higher than the transfer of the yoga. So as a coach, what you're thinking is, I would like to create training programs that are all effective in transferring skills. Why waste my athletes' energy doing things that don't make them better? Coaches do that a lot because they don't actually measure it. Okay, so the first thing I need to do before we go on to look at the math behind figuring out the exact amount of transfer that's happening in any particular activity is to remind you of the normal curve. That is why this is the normal curve. And I want to remind you that the normal curve is set up when we take the mean, whatever it is. So if I test 20 players and their average squat is 100 kilos, 100 kilos would be right here at the mean. These values down here are standard deviations. And so the average of my people was 100 kilos. Let me get my pen. So the average was 100. But not every athlete, I don't remember how many I told you I tested, 20 athletes, and the average is 100 kg. Oh, forget the kg. But not everybody tested exactly 100. That's an average. So we can use Excel, or we can use, there's things on the internet. You can calculate it by hand if you can look up the formula. We have the standard deviation, which is always expressed, or usually expressed as plus or minus the mean plus or minus the standard deviation. And so let's say that in our 20 athletes, the standard deviation was, I don't know, let's do 10. Let's keep it very round for my mathematically trained, challenged brain. So the mean was 100 and the standard deviation was 10. That means that this value is 110. 10 higher, 1 standard deviation higher. So 34% of my athletes were between the mean and 1 standard deviation above the mean, which is 110. Why do I know it's 1 standard deviation above? Because I told you 10 is the standard deviation. 34% of my athletes are going to be between the mean and 1 standard deviation below. Well, that would be 90. So 34% of my athletes on average, this is what standard deviation means. On average, 34% of my athletes should be in that range if it's a normal curve. And we just continue this out. So 2 standard deviations is 80. So 80. So 13.5% of my athletes are likely between 90 and 80. And then you go over here and you do this one and you get the idea. This would be 130. And the other one would be 70. So I have a small number of athletes who are going to perform really high and a small number of athletes who are going to perform really low. And most of the people are going to fit in the mean. That's what the normal curve means. Do you now remember what standard deviation is? Because in order to calculate how helpful something was, I gotta roll this again. All right. I'm gonna go down here. I'm gonna scooch ahead to, this is from the textbook, page 8 and 9. If you want to pull it up on the textbook instead. So this is a research study, and it's a research study that looked at transfer. And so let's walk you through it. In this research study, and this is why you need to listen, because this is not exactly obvious the way it's written in the book. In the research study, what they wanted to know was, like let's say I have power lifters, and so squat is their sport, and getting a higher squat means they're winning in their sport. You with me? Now, I want to know what training methods, so my performance characteristics is squat. And if I can get their squat maxes up, that's what I want. That's performance. But my training variable is, well, I'm actually interested in using isometric exercise. I'm just going to put ISO. My training method is ISO. I'm going to do isometric squats in 2 different ways. And I want to know which one is going to improve their squat more. So I'm going to have my athletes who squat all the time, but I need to change things up. I can't just have them squat. They'd reach their, they would reach plateau. They would get diminishing returns over time. So I got to come up with more ways to train the squat besides just squatting. So I'm going to use isometric squat. Now, this is what the isometric squat is. You're going to go to a squat rack and you're going to set it so that when you are pushing up, the bar is pushing on the stops. So instead of taking the bar out of the rack, you're gonna keep the bar in the rack. And when you push up, it bar does not move. That way I can push up as hard as I can, but there's no movement, so it's an isometric squat. Now, when you're doing isometric squats, you can't change the weight because the weight is controlled by my brain, my motor units. All you can change is where you set that bar. If I have a squat rack and I set the bar pretty high, so I'm almost fully extended, my legs are almost straight, just slightly bent, like a quarter squat position, this would be right here. And that's what this arrow indicates. These people basically set up their isometric squat rack so that they did quarter squats, not very much knee bend. And the other half of the people, they set up theirs with, over here, they set theirs up to do a very, very deep squat. So they are trying to do squats with much more knee bend. You can see here's the knee angle, right? So these people are like way down below parallel, and they're trying to push up against the bar, which will not move because it's set to it's isometric, but they're in a really deep squat position. Okay, so far so good. We're going to do isometric squats as our training activity. I want to increase the squat strength of my athletes because that's what we're training for. And I have two different ways I want to compare which one's going to work better, which one's going to transfer better to the squat. And so here we go, before and after. Well, the people who were the deep squatters, the deep isometric squatters, you can see that before, that was the amount of force they were able to generate. How would you measure this? You could just put a scale under their feet and see how much they push into the ground, but they're very expensive scales that we have to do this exact purpose. So these people obviously have nice equipment in their weight room. But so at first, they were very weak when they were in that bottom position. But over the course of training, after the training, so I don't remember how many weeks this was, 6, 8, 12 weeks, whatever, they were much stronger. You can see that they could push harder into that bar that does not move. And what they're doing here is they're measuring not just the joint angle that they trained at, they measured several joint angles, even lower, all the way up to standing up. Now, interestingly, we're going to learn about this later, specificity. We know that when you train isometrically, the angle of your training is going to be specific. So the people who trained at the higher knee angle, the more straight, the quarter squat position, they get more benefit in this part of the graph. As you can see in that part of the graph, they're pretty close together comparatively. And then these people got more benefit here, and these people were really close together in that part of the graph here. So specificity is also being shown in this graph. Okay, so before training is the dotted lines, and after training is the straight line. You can see that both groups improved their the amount of force, that's Newton's force, that they could generate during the squat. And they both improved it at all the different joint angles. However, there were some differences in which joint angles were strongest. Okay, but it still doesn't tell me which one makes for better transfer. All right, so let's get to the math here. I got it. Go back over here and let's go back up and let's look at the math. The formula for result gain, formula for result gain is gain of performance divided by standard deviation of performance. And now I'm going to erase all of these notes that I left you. Sorry. All right. So the result gain in this situation, now we gotta scroll, whoops, scroll. All right, the result gain in this situation, you can look right here. If for the people who were squatting at 70 degrees, the deep squats, you can see we took the mean before and the mean after, and here is the gain of performance. So there were 410 newtons gain plus or minus 170. So on average, the people who did the deep squats were able to push with 410 newtons more than they did at the beginning. But not everybody pushed 410 newtons more. Some people pushed a lot more, some people pushed a little more, and we could create a little normal curve using this mean and standard deviation. So to find the result gain, we use the formula I just mentioned above, which you can find on your sheet. You can find that sheet. And then you can see they took 410 divided by 340. 410 was the mean increase, and it's divided by the initial standard deviation. And you can see that the result gain for this deep squat was 1.2. That is a unitless measure. There is no unit to 1.2, but it allows us to compare different types of exercises to each other. So you can actually compare the Newton force of doing this to your plyometric program, which doesn't have newtons. All right. Now, the same thing was done for the high force angle. And you can see, blah, blah, blah. They found the difference, and they found the standard deviation of the difference. And here's what they did. They took the mean improvement divided by the initial standard deviation, and you can see that it's 0.91. So the first thing we already know is the result gain that the deep squat position produced more improvement than the high squat position in newtons. Okay, that's awesome. Fantastic. However, that didn't say anything about whether it was going to make my people squat more. You see, there was no, this is just the Newton forces at those particular angles. It didn't tell me whether they were going to be better on their powerlifting competition. I need to do one more set of calculations in order to figure that out. And so in this study, not only did they measure how much force they produced at these knee angles, they also just took their squat maxes before and after. And this happens many, many times in your research. And research, when we do research for our team, we that is a type of research, type of field practical research. And so yeah, this happens all the time. This group had a starting squat of 95. This group had a starting squat of 102. They weren't the same. So we can't compare apples to apples. They weren't the same. Both groups increased. 95 went to 107, 102 went to 110. But we can actually calculate all that out and get rid of all the, differences in individuals and get a single number. And so here's how we do that. Next formula we need is this one right here. Whoops, where is it? November. Transfer. Transfer is the result gain in the non-specific exercise divided by the result gain of the sport-specific exercise. Remember, we tested both. The non-specific exercise was the Newton's force when we were doing the isometric squats. And the sport-specific exercise for these powerlifters is the squat. So I'm going to go back down here. They took the result gain of here you can see right here. They found the result gain of the squat for this group and the result gain of the squat for this group using the exact same process we just went through. Rewind me if you need it. And now we're going to do the result gain of the sport-specific 0.05, see here, divided by this result gain of the non-sport specific activity, 1.2. And so that gives me a 0.42 transfer value. That's pretty good. That's pretty good. Let's compare it to the people who did just the quarter squats instead of the deep isometric squats. In this case, the result gain for them, again, you can go rewind and see how they calculated that, was calculated here at 0.27. The result gain for the sport-specific activity divided by the result gain of the non-sport specific activity gives us a transfer value of 0.3. So which one is the better activity? And you can see that here. You can see that here. But my takeaway from this as a coach is that one, the deep squat isometric squats, the deep isometric squats, not only produced a higher change, 0.12 compared to 0.91, not only produced higher changes in just the Newton forces of that activity, it also produced the higher improvements in my sport-specific activity. So now I, as a coach, know that comparing a quarter squat isometric quarter squat to an isometric deep squat is not only a more activity, a training activity that's going to produce more fitness, it produces more performance for this particular set of athletes. Now I know which type of isometric squats I'm going to spend more time on. I might still include isometric squats at the higher value some points during the season, but I know which one is going to give me the biggest bang for my buck. And so I'm going to add deep isometric squats for this particular group of athletes because that is what produced the greatest effect for them. Remember that as a coach, if you do this on the team you coach in in 2023, then you know that information and can apply it to the student, to the athletes in 2024, 2025, 2026, and then just periodically test all of your training methods to know if they are producing the benefits that you think they are. It's what a good scientific coach would do. It's we'll start referring this semester to strength coaches as sports scientists. And this is why you see they're sports scientists. They're doing their own little research on their own little subjects. Now, mostly people don't publish this because you don't really want to share this information. This is what makes your athletes better than those athletes over there. So you don't want to share this information the way we share some other research. This is just for you to become the better coach. All right, so I have put in here another little example. To this one, you're just going to calculate result gains. I gave you a little example of some cross-country runners, and they're working on their lactate threshold. And I give you some values and standard deviations, some means and standard deviations of their lactate threshold. And I want you to calculate the result gains and then calculate the transfer to tell me which mode of training, resistance training or extra running, is going to be the go-to method that I'm going to use as a coach for these particular athletes that I get. All right. I know that's a lot. Rewind. It's okay. Rewind and listen again. Go through it step by step. And the book also has information in it. You can do it. Last kind of page of concepts. Now, I'm actually going to fast forward here. This is the general adaptation syndrome. I harped on this. I harped on this. I harped on this. We made this the central theme of our 260 class. You can't forget it. I put it here in case you did. Read it, refresh. Selye's general adaptation syndrome and all the different phases. You got the alarm phase where it goes down, and you got the resistance phase where your body's building back up, and you got the super compensation phase where you get stronger than you were before. And then if you don't do anything, it's going to, detrain. But we have definitely want to avoid overtraining, which is so much stimulus, I break you and you can't recover. Remember this? Okay. Now, this book is going to cover some of these other models, which are considered alternate models, or I'd say basically everybody knows both models and everybody kind of picks one that's their go-to. So if you work for or your internship director uses this model, you should know the terms of this model. It's similar. We are going to have the same kind of thing during the workout. The workout is the black bar. Here's the workout. You start out at a particular fitness level, and the workout makes you tired and depleted. That is your depletion phase, similar to the alarm phase. Then you have the restitution phase, similar to the resistance phase, where your body is building back up. Super compensation, they use the same word. Thank God. All right. Notice that this model is simplified in that it only focuses on improvements, doesn't address overtraining. So this is called the fitness and fatigue model. And this is one of the ways we look at the fitness fatigue model. Now, remember from I showed you this kind of graph exactly the same way in 260. We can arrange our training loads in order to produce particular changes. So for example, I could have a training load and let you not fully recover, another training load, not fully recover, and another training load and not fully recover. And then you end up down here over time. So you either need rest days or I am going to have an overtrained athlete. I could put more time or shrink up the stimulus so that it didn't challenge you so much. So then you would go down and you would super compensate in time for the next workout. And so here you can see the pattern of exercise and super compensation. This is most likely a beginner. In a beginner, you can have one workout, let them super compensate, and they're better the next time. That doesn't work for advanced athletes. Here's an unfortunate situation, our weekend warriors, where they work really, really hard and they get really beat down, but they recover because they take 5 days off and super compensate, but their super compensate decreases, it detrains before their next workout. So they're really challenging their body, but because of bad timing, they're not getting any benefits, never getting benefits. And then here's a really fun one. This is actually what we do to athletes who are more advanced athletes. We give you a training load. This is a very small training load. This might be a morning workout and then a afternoon workout and then the next morning a workout, and you definitely didn't recover in time. But then I give you the evening off and the next day off, and you're super compensated for your next workout 2 days later. So this might be kind of a training method we might use with a more advanced athlete, or just to switch it up during part of the year. All right, last, we're so close. This is a 2-factor model of fitness and fatigue, and it basically shows the same thing in a different strategy, and it introduces the idea of preparedness, which is actually a formula. I didn't put it in here because it's a super complicated formula. I don't know anybody who actually calculates it. It's more of a concept. But the idea here is that after a workout, your fitness is down and your fatigue is high, but your fatigue will return to baseline and your fitness is going to return to baseline. And your preparedness is a formula that takes into account your initial fitness, how hard you worked at your last workout, so how fast you're recovering, a whole bunch of different things. And so essentially, it's the fitness and fatigue that we just already looked at, and a new concept, preparedness, a way to calculate how ready you are to face a new challenge. Very simply, during this part of the graph where preparedness is low, you are beat down, you are in the resistance phase, you are not super compensated, you're below your normal performance. But when you get to this place where the fitness is returning to its baseline and the fatigue is returning to its baseline, then our preparedness is up. And so anytime preparedness is above this baseline, that means that you are in a super compensation phase. So we would want to time your workout or your competition so that you are in a super compensation phase. New graph, same concepts. All right, what you then have down here is some questions, and you saw along the way, you have to go in and put notes in. You will fill this out and you will either take a picture if you do it by paper, or you can type into it. Please use a different font color so I can see what you've added really easily. You get, there are specific things I'm looking for. Did you answer these questions? But mostly I just grade these for completion. So if you do a half-assed job, you get a half-assed grade. And if you do really good diligence, where this is going to be an amazing set of notes for you moving into the rest of the course, then you'll get your full points. All right, reach out by email or come see me in the office hours this week if you're struggling. You do have quite a few assignments this week. We do not cover 3 chapters every week, but the other 2 chapters are much easier. You're going to be fine on your own. All right, I'll talk to you soon.